Good evening, everyone. I am Shivani Dhok and I welcome you all for the week 12 tutorial for the course of Introduction to Wireless and Cellular Communications. So, this is the week 12, that is the last week for this particular course, and like every week, this week's tutorial will be divided into two parts. The first part will be recap of the content that we have covered in the week 12, followed by the questions which are related to that particular content. Before I start with the recap of week 12 content, a small note I would like to make is this Sunday, that is on 12th of October at 3 p.m. I'll be taking a summary session in which I'll be revising all the content of this course. I won't be solving any questions. I will be just revising all the concepts that have been covered in this course. Hope to see you on Sunday as well. Okay, so let's quickly start with the recap of week 12 content. So week 12 was all about MIMO. MIMO, which is basically multi-input, multi-output, multi-input, multi-output systems. And what do we mean by my multi-input, multi-output with respect to communication systems or wireless communication? It means that your transmitter is equipped with multiple antennas as well as your receiver is equipped with multiple antennas. So you have multiple antennas. So let's say you have NT number of transmit antennas. So this is my transmitter. And I have NR number of receive antennas. Let's say this is mth transmit antenna. This is nth receive antenna. Yeah. So you have, okay, this is my receiver. So I have NT number of transmit antennas. And NR is my number of receive antennas. So this is NR. So this is the setup, and this M, the channel between your mth transmit antenna and nth receive antenna, it is given by HNM. Okay, so just to write again, HNM is your channel between mth transmit antenna and nth receive antenna. Okay, and this nth antenna, at the nth receive antenna, we are still discussing MIMO channels. What do we receive? We receive signal YN, and Yn is given by your summation M equal to 1 to all of your transmit antennas, H of Nm into X of M plus N, Nn. Yeah. So this is what you will be receiving at the nth receive antenna, and this is your AWGN noise. Now when we stack all of these y's in a vector, we get a vector y. So we'll have y1, y2 and so on till yn are, yeah. So this is given by h11, H12 and so on till H1NT, H21, H22 and so on till H2NT and so on. And for the last antenna, that is NRX antenna, it will be HNR1, HNR2 and so on till HNR, HNT, multiplied by all the signals transmitted from different antennas. It will be X1, X2 and so on till XNT, plus you will have N1, N2 and so on till NRX. So this is your channel matrix H. So this is of dimensions NR cross NT. This is your transmit vector, that is X. This has a dimension of NT cross 1, and this is your noise vector. This has a dimension of NR cross 1, that is number of transmit antennas cross 1. We are still discussing MIMO channels. So what we have is, okay, what I'll do, I'll add a page here instead of just repeating. Yeah. Okay, so what we get here is y equal to hx plus n. So this is the MIMO receive equation. And the problem that we want to solve here is how to, okay, given h, how to estimate, or let's say detect what was transmitted, that is x. And next question is, what is the capacity? Of this MIMO channel. Okay, so this is what we tried to answer here. We didn't look at detection rules, but you can very well construct different types of receiver, ZF receiver and all those things. We didn't go into those things, but what we looked at was how this channel H, how we can play with this channel H, and what are the capacity of this MIMO channel. And to do those things, we looked at a very important concept, mathematical concept, that is known as singular value decomposition, or what we call as SVD. So the singular value decomposition of the matrix H, so SVD of a matrix H is given by H equal to U sigma V Hermitian, where this U, this contains the left singular vectors of H, which is equivalent to eigenvectors of HH Hermitian. This V is right singular vector of H, or it contains right singular vectors of H, and this is equivalent to finding eigenvectors of H Hermitian H, and this matrix sigma. Okay, so before I go ahead, let's say this H is of dimension, let's be consistent, NR cross NT. So this U will be of dimensions NR cross NR. This is unitary matrix. These are unitary, both of them. What do you mean by unitaries? U Hermitian and U Hermitian U both will be identity matrix. Similarly, V Hermitian and V Hermitian V will be identity matrix. And the dimension of this V will be nothing but NT cross NT. And therefore this matrix sigma will be basically NR cross NT dimensional matrix, and it is some sort of diagonal matrix which has sigma 1 and so on till sigma L, rest everything is 0, and you will have a 0 matrix here, 0 matrix here, 0 matrix here. And here L is nothing but rank of your matrix H. So what are these values? Sigma i's. Yeah. So here this sigma I is known as the ith singular value of H, and sigma 1, and these are ordered, so these are in the descending order. So sigma 1 square is greater than or equal to sigma 2 square is greater than or equal to, and so on. Sigma L square greater than 0. These are non-negative, and yeah, L is rank, so these are positive. And the sigma I square, these are basically non-zero eigenvalues or ith non-zero eigenvalue of H Hermitian H or H Hermitian. Okay. So this is essentially our singular value decomposition, and we used this singular value decomposition to get something known as the parallel decomposition of MIMO channel. So if you go back to our MIMO equation, whatever we have here, so we were transmitting X and receiving Y. So now we said instead of transmitting X, we'll transmit something else. So we'll transmit a rotated version of X, that is we will now transmit, so we will now transmit X tilde, which is your which will be basically your Vx. So what will you receive? We will receive Y tilde, which is X tilde plus N. Noise vector remains same. And now I can use singular value decomposition of my matrix H, which is U sigma V Hermitian, and this X was essentially V into X plus N. Yeah. So now since V is unitary, V Hermitian V is identity matrix. So what we are left with is U sigma X plus N. And once we have that, what we'll do, so this step here is known as yeah, so this particular first step, it is known as pre-coding. And now what we will do, we'll do combining. And for combining, we'll construct our vector Y, which is U Hermitian Y tilde. And then this will give me U Hermitian U sigma X plus N, which is equal to, again, U is a unitary matrix, so U Hermitian U is I. So what I'll get is sigma X plus N, and mind you, sigma is a diagonal matrix. So this is basically giving me something like this. So I'll have y1, y2 and so on till ynr. That will be equal to sigma 1, sigma 2 and so on till sigma L. Rest is 0. And I'll have x1, x2 and so on till xnt. Plus I'll have, so let's say n tilde, n1 tilde, n2 tilde and so on till nnr tilde. And this is basically equal to sigma 1 x1, sigma 2 x2 and so on till sigma L xl, and then I have zeros, a vector of zeros, plus I'll have noise. I'll have N1 tilde, N2 tilde, and so on till N and R tilde. So now I have parallel decomposition of channels. I have L parallel channels because from L plus 1 to NR it will be 0. So I have L parallel channels, and hence this particular structure is known as the parallel decomposition of channel. And then we use this parallel decomposition to figure out the capacity and all those things. But before discussing capacity, we looked at the basic concepts of information theory, which are entropy, in mutual information, and capacity. So entropy, the basic definition that we looked at was for discrete case, it was, let's say, if x is a discrete random variable, then h of x is simply minus I equal to 1 to m. It is a finite alphabet. Then pi into log of pi, where pi is the probability of ith entry. And if this is also equal to expectation, and when we have a continuous random variable, then h of x is basically minus of expectation of log of fx of x. So this we had seen. Then mutual information, that is x of I comma y. That is how much information do we get when we are observing y about x or x about y. So this is equal to h of x minus what is the uncertainty in x given we have observed y. This is also equal to, it is a symmetric thing, so h of y minus h of y given x. And capacity is based on this mutual information. So this capacity is basically maximization of your mutual information with respect to the distribution of either x or y based on what definition you're taking. Okay, so this was all about related to capacity, mutual information, basic definition. And then we said that we know the definition of AWGN channel. We know the capacity of AWGN channel. Then how does the capacity of MIMO channels look when we have such kind of parallel decomposition? So the first thing that we looked at was capacity of MIMO channels based on, so this particular thing that we first looked at was based on parallel decomposition of MIMO channels. And we said that capacity for this is given by, when I know the channel, it will be simply addition of all these capacities log to 1 plus rho sigma I square into pi, where sigma I square, where rho is the SNR of AWGN channel. This we saw, and then we said that, okay, so this particular equation here is function of power pi. Pi is the power with which I'll be transmitting my symbol xi. Okay, so now the question that arises is how to set up optimally these PIs. So we had already seen an algorithm, and when we were solving this particular optimization problem, that is maximizing this capacity for under a power constraint, we saw that this again results in a water filling kind of situation. So we want to allocate, I'll just write it, allocate PI such that maximum power constraint to PI to maximize capacity such that the power constraint I equal to 1 to L PI less than or equal to P is satisfied. And we saw that this again takes us back to water filling. So I'll be looking back, we'll be taking up a question. So I'll be taking a question which is related to all these things. MIMO channel and its capacity and how to allocate power. A simple question I'll take. Okay, so we have these things, and now what we are going to do is the next thing that we discussed is the ergodic capacity and the log-det formula for the capacity of MIMO channels. So this log-det capacity is given by, I won't be looking at getting into details of how it was derived. I'll just write it down. Just start from here. We are discussing log-det formula. This is capacity, this is ergodic capacity, expectation over the channel gains, log to the base 2, determinant of INR plus sigma x square upon sigma n square into HH Hermitian. Yeah, this is our log-det capacity. And after that, we looked at the special cases of MIMO. That is when I have NT equal to 1, I'll get receive diversity. And this is our CMO case. And then we looked at NR equal to 1. And we have multiple antennas, so I'll have transmit diversity. And this will basically give me my meso case. And we saw that whatever observations we had with our basic understanding of diversity, same things follow when we looked at them through MIMO perspective. So this was all that was covered in week 12. If you have any questions, then let me know. Otherwise, I'll go ahead with the questions that I have planned to cover today. Okay, if there are no questions, then let me move on to the questions that I have planned to cover today. So these questions might be a little bit, some questions will be similar to what is required or what are there in your assignment, and some questions are conceptual for your better understanding of MIMO and basic information theoretic aspects. So let's start with the first question. So it says that consider a finite alphabet S which has total 5 letters, that is A1, A2, A3, and A5, where probability of A1 and A2 is 0.25. So probability of A1 is 0.25. Probability of A2 is also 0.25. Then probability of A3 is given to us as 0.3. And then probability of A4 and probability of A5 both are 0.1. Yeah, so this is given to us, and what we need to find out is the entropy of this particular alphabet. So we want to find h of this alphabet S. So by definition, h of S will be given by minus of summation I equal to 1 to 5 P of AI into log to the base 2 P of AI. Okay, so this is what we need to find out. So what we'll do now is we'll just simply substitute those values. Let me add a page. So h of S is, I'll just repeat the formula once. that is summation I equal to 1 to 5 with a negative sign, probability of AI into log of probability of AI to the base 2. This is given by a minus sign outside. Then I have A1 has a probability of 0.25. So 0.25 into log to the base 2, 0.25. And we have yeah, then plus we have 0.25. This is for A2, 0.25. Then for A3 it is 0.3. So I have plus 0.3 log of 0.3 to the base 2, plus I have A4 is 0.1, so 0.1 log of 0.1 to the base 2, plus A5 is also 0.1. So this is what we have. Now again, if we use our calculators, this 0. Log 2 of 0.25, this comes out to be equal to 2. Minus 2. Then log of 0.3, this comes out to be equal to minus 1.7370, and log of 0.1, this comes out to be equal to minus 3.3219. So if I substitute these values in this equation, what I am left with is minus of 0.25 into minus 2, that comes out to be equal to minus 0.5, again minus 0.5, minus 0.5211, minus 0.332219, and minus 0.332219. Sorry, 219. Yeah, and again this comes out to be equal to 2.1855 bits per channel use. Is this clear? This is a simple application of entropy formula. Any questions till this point? Okay. If not, then let me move on to the next question. It says that repeat question 1 if all the symbols in S occur with equal probability. So what it means is we had, so this S, I'll just repeat, it had 5 symbols, that is A1, A2, A3, A4 and A5. And now all of these occur with equal probability. What does that mean? It means that probability of AI is equal to 1 over total number of values, that is 5, for all I in 1, 2, 3, 4 and 5. Okay. So now what we need to find out? We need to find out H of S, which is nothing but summation I equal to 1 to 5 probability of AI into log of probability of AI to the base 2. Then probability of AI is 1 over 5. So this comes out to be equal to minus summation I equal to 1 to 5, 1 over 5 into log to the base 2, 1 by 5. Now this is nothing but 5 minus of 5 into 1 by 5 into log of 1 by 5 to the base 2, and if you simplify, this comes out to be equal to 2.3219 bits per channel use. Is this clear? One small observation I would like you to do, make is, in the previous question when we found out the entropy, the symbols were not equiprobable. So the entropy that we got was 2.1855. Okay, and when these symbols became equiprobable, the entropy that we got is 2.3219. So this value is higher compared to the entropy that we got in the previous question. What does so in general, I'm not proving that, just take it as a fact. You will have a good proof of this in information theory course. So just a takeaway that you can have is, if S is an alphabet which has A1, A2 and so on till AM, which means M symbols, then H of S will be maximum when probability of AI is 1 over M for all I, which means that the symbols are equiprobable. So you can understand this in this particular way, that entropy measures the degree of uncertainty. So if all the symbols are uncertain or equiprobable, so there is a higher degree of uncertainty. So the entropy should be higher. There are good proofs for this in information theory course. I am not going to get into details of that. Okay, is this clear? Any questions? Okay, if not, then let me move on to the next question. So here it's the question is, find the mutual information of a BSC with a crossover probability of P. What do we mean by BSC? So this BSC stands for binary symmetric channel. Okay, and what do you mean by this binary symmetric channel? So binary symmetric channel means you have two inputs and two outputs. So one output will be 0, one input will be 0, another input will be 1. Let's say input is given by X, and then you have another input, you have one output as 0 and another output as 1. Let's say the output is given by Y, and this 0 can flip to 1 or have a crossover to 1 with probability, the crossover probability as P, and the 1 can flip to 0 with the same probability. That brings the symmetry again with probability P, and this 0 can stay as 0 with probability 1 minus P, and similarly 1 will remain 1 with probability 1 minus P. So what are these probabilities? These probabilities are basically probability that Y becomes 0 given X was 1, or let's say X was 0. That probability is given by this particular probability. This is transition probability. It's a conditional probability. It is given by 1 minus P. Then probability that you observe the output as 0 given you have transmitted 1. So that means your bit is flipped. So this has a probability of P. Then probability that you observe Y equal to 1 given you have transmitted 0. So again there is a flip, which means you are transitioning from this 0 to this 1. So therefore this has a probability of P. And similarly, probability that you're observing y equal to 1 given you have transmitted x equal to 1, which means there is no error, there is no flipping, there is no crossover. So the probability is 1 minus p. So this is a standard way of representing the binary symmetric channel. So now what is asked us is find the mutual information of this binary symmetric channel. Okay, so mutual information okay. So this mutual information, that is I of x, y, it is given by h of y minus h of y given x. Okay. So yeah. So what all things do we need to find out to find I of x comma y? So we need to obtain h of y, and second thing is h of y given x. Okay, so let us first find out h of y. So now this y, um, yeah, let me write it in this way, h of y. So this y is a binary variable or binary random variable. So let's say that probability of y equal to 1 is alpha, then probability of y equal to 0 will be basically 1 minus alpha. Okay, so now what will be my h of y? H of y will be equal to minus probability that y equal to 0 into log of probability of y equal to 0 minus probability of 1 into log of probability of y equal to 1. So this is nothing but minus of 1 minus alpha log to the base 2 1 minus alpha minus alpha log to the base 2 alpha. And this is a standard function in information theory, and people refer to this as little h of alpha. Now what is this alpha? This alpha, which we know, is probability that y equal to 1. Now I can write this as probability of y equal to 1 given x equal to 0 into probability, let me be consistent with my notations, x equal to 0 plus I have probability that y equal to 1 given x equal to 1 into probability that x equal to 1. Now probability of y equal to 1 given x equal to 0 is what? Y equal to 1 given x equal to 0 is p. So this is p into probability that x equal to 0 plus y equal to 1 given x equal to 1 is 1 minus p into probability of x equal to 1. So when you know what are the probabilities of x equal to 0 and x equal to 1, you can then accordingly find out the value of alpha. So this is how you will find out h of y. But h of y equal to h of capital H of y equal to small h of alpha is sufficient information that we will require. The next thing that we need to find out is, okay, so we found out h of y. This is done. The second thing that we need to find out is h of y given x. So now we'll find out h of y given x. What do you mean by h of y given x? This is a conditional entropy, or entropy of random variable y given a random variable x. Okay, and given x, I can obtain as h of y given x equal to 0 into probability that into probability that x equal to 0 plus h of y given x equal to 1 into probability that y equal to 1, sorry, x equal to 1. Okay. Then what do you mean by h of y given x equal to I? This is entropy of random variable y given an event that x equal to I, such that I where I belongs to 0 and 1. Okay, and h of y given x equal to I is given by minus of probability that, okay, y equal to 1 given x equal to I into log to the base 2 probability of y equal to 1 given x equal to I minus probability of y equal to 0 given x equal to I into log to the base 2 probability of y equal to 0 given x equal to I. So now let us find out all of these for what the cases that we have. So h of y given x equal to 0, that will be equal to minus of probability that y equal to 1 given x equal to 0 into log of probability of y equal to 1 given x equal to 0 minus probability that y equal to 0 given x equal to 0 into log to the base 2 probability of y equal to 0 given x equal to 0. Now probability of y equal to 1 given x equal to 0 is what? Probability of y equal to 1 given x equal to 0 is e. So this is minus p into log to the base 2 p minus y equal to 0 given x equal to 0 is 1 minus p into log to the base 2 1 minus p. So this is nothing but little h of p. Now similarly, I can find h of y given x equal to 1. This is given as minus of probability of y equal to 1 given x equal to 1 into log to the base 2 probability of y equal to 1 given x equal to 1 minus probability of y equal to 0 given x equal to 1 into log of probability of y equal to 0 given x equal to 1 to the base 2. Now probability of y equal to 1 given x equal to 1, that was 1 minus p. So I have minus of 1 minus p log of 1 minus p to the base 2 minus probability of y equal to 0 given x equal to 1 was p log of p to the base 2. Now I can so this is also equal to your little h of p. So both of these things are equal to little h of p. I can substitute them back in h of y given x. So therefore h of y given x comes out to be equal to h of y given x equal to 0, which is h of p into probability that x equal to 0 plus h of y given x equal to 1, which is again h of p into probability that x equal to 1. Now I can take h of p common. That gives me probability of x equal to 0 plus probability of x equal to 1. This x is also a binary random variable. It can only take two values, which means that the probability of x equal to 0 and probability of x equal to 1, this quantity here is equal to 1. There are no other values. So therefore, h of y given x comes out to be equal to h of okay. So now I have h of y given x. I had already obtained h of y. So now I can get my mutual information as h of y minus h of y given x. So therefore, mutual information, that is h of x given x comma y, is capital H of y minus capital H of y given x. H of y, what was it? It was equal to h of alpha or little h of alpha. Yeah, this is h of alpha, and h of y given x is equal to h of p. So I have minus of h of p. So this is the mutual information of your binary symmetric channel. Is it clear? Any questions? Okay. If that's clear, then let me move on to the next question. So it says that find the capacity of binary symmetric channel with crossover probability as P. So what is your definition of capacity? So your capacity C is maximize your mutual information, and this has to be done with respect to either distribution of x or distribution of y. Okay, so let's say I want to do it with respect to distribution of y. Okay, now we had seen that this max of p of y is nothing but your h of alpha minus h of p, and your p of y is a function of your alpha, so I can simply replace it as alpha. Now this is a binary symmetric channel. This crossover probability p, this crossover probability p, or rather this p is your crossover probability. This is the property of your channel. Which means that you have no control on P. So the only thing that you can control is your alpha. The only thing that we can control is alpha. And what was alpha? Alpha came out to be P into probability of x equal to 0 and 1 minus P into probability of x equal to 1. So this alpha is P into probability of x equal to 0 plus 1 minus P into probability of x equal to 1. And let's say probability of x equal to 1 is some q. So therefore your alpha, let me add a page, I don't want to write it here. Yeah. So you have alpha equal to probability, so P into probability of x equal to 0, that is 1 minus q, plus 1 minus p into probability of x equal to 1, that is q. Now again, you don't have control over this p, so this is not in your hand. So now to control alpha, you will have to control q. So to control alpha, we need to control q, which is the distribution of your input x. Okay, so this is how things go. But now what we'll do is we'll first try to get the value of alpha that maximizes the capacity. So this value of c, this capacity which is max over of this particular thing over alpha, I can also write as, therefore the c is equal to basically max of alpha into h of p, h of alpha minus h of p. Okay, now h of alpha is what? H of alpha is h of y, and this y is a binary random variable. Okay, and when we were solving the previous questions regarding entropy, we saw or I made a note that when you have an alphabet with, let's say, m number of symbols, then the entropy is maximum when all the symbols are equiprobable. Now, if we want to map the same idea to what we are doing right now, for our case, this m is equal to 2. So I have a1 and a2, where a1 is, let's say, 0 and a2 is 1. So my entropy of y will be maximized when probability of 0 is 1 and probability of 0 is half and probability of 1 is half. So this little h of alpha is maximum when alpha is equal to half. That is 0 and 1 are equiprobable. Okay, so this is what we have already seen. So therefore, your h of half comes out to be equal to, or let me just write it down once. H of alpha was minus 1 minus alpha log to the base 2 1 minus alpha into log of alpha to the base 2. So if my alpha is equal to half, so h of half is minus half into log to the base 2 half minus half into log to the base 2 half, which is nothing but minus 2 times log of 1 by 2 to the base 2, which comes out to be equal to into half. Sorry, this gets cancelled, so this comes out to be equal to 1. So therefore, if I substitute it back, therefore my c comes out to be equal to 1 minus h of p. So this is the capacity of binary symmetric channel with crossover probability as p. Okay. Another thing is, now you want to control your alpha, and that can be done by controlling your q. So let me just do that also. So we have alpha equal to, and just write it as star. So this alpha star is equal to half, that maximizes your entropy of y. So this alpha star will be equal to p into 1 minus q star plus 1 minus p into q star. This is value of q that maximizes c. and this is equal to your half. So now I can write this as P minus PQ star plus Q star, yeah, okay, leave it, yeah, plus Q star into 1 minus P, which is equal to half. So this P I can keep it as it is, minus Q star I can take out common. I'll have P minus 1 plus P is equal to half. So I'll have P minus Q star into 2P minus 1 is equal to half. So this I can write as P minus half upon, let me just do this first. Yeah, P minus P plus Q star into 1 minus 2P, which is equal to half. So this Q star now comes out to be equal to half minus P upon 1 minus 2P, which I can write as 1 minus 2P divided by 2 whole divided by 1 minus 2P. This gets cancelled and what I am left with is half. So if I substitute Q equal to half in this equation above, I'll be left Q star equal to half. So this is the value of, so if again my inputs are equiprobable, I'll have a maximum capacity. So this is what we are having here. Any questions till this point? Okay, if not, then let me move on to the next question. So it says that find h of x if x is distributed as a Gaussian random variable with 0 mean and variance sigma square. So this h of x is given by minus of expectation of fx of x. And how does your fx of x look? Your fx of x, it is given by 1 upon under root of 2 pi sigma square into e power minus x square by 2 sigma square. Sorry, I made a mistake here. Wait. This is not this. This has a log to the base 2. Yeah. Okay. So now if I take log to the base 2 fx of x, this will give me minus half of log to the base 2 2 pi sigma square minus I'll have log to the base 2 e power minus x square by 2 sigma square, plus. This comes out to be equal to minus half log to the base 2 2 pi sigma square minus x square by 2 sigma square log of e to the base 2. So now if I substitute this in the equation of my entropy, so what I get is h of x is equal to minus of expectation of log of fx of x. So this is equal to minus of expectation of this log of fx of x is minus of half of log to the base 2 2 pi sigma square minus x square by 2 sigma square log e to the base 2. So the only random variable in this equation is your capital X square. So rest all are positive. So this comes out to be equal to, also there is a minus sign outside, so if I take it inside, everything becomes plus. So this is half of log of 2 pi sigma square plus expectation of x square upon 2 sigma square log of e to the base 2. Now this thing, expectation of x square, is given by your variance of x plus expectation of x whole square. So variance of x is sigma square and mean of x is 0. So this comes out to be equal to sigma square. So therefore h of x is half of log 2 pi sigma square to the base 2 plus sigma square upon 2 sigma square log e to the base 2. This comes out to be, this gets cancelled and I can take out half common. So I'll get log of 2 pi sigma square plus log of e to the base 2. This comes out to be equal to half of log of 2 pi e into sigma square. So this is the entropy of a Gaussian random variable with 0 mean and variance sigma square. Is this clear? Any questions? Okay. So this is all about your mutual information capacity and all those things. Now I'll switch gears to MIMO. So what I'll do is I'll take up a toy example of a MIMO channel. Then we'll try to represent that particular MIMO channel in parallel decomposition form. And then we'll find its capacity. And then we'll try to allocate powers to these different eigenmodes. Okay. So let us start with the first question of this particular thing. Series of questions. So from question number 6 to I think till question number 10, we'll be doing all this business. Okay. So let's start. Consider a MIMO channel given by the matrix H equal to whatever is given here. And then find the singular values of H and what is the rank of H. Okay. Now you are given this matrix H. This is a 3 cross 2 dimensional matrix. Okay. And singular values of H are basically, or let me say it in this way, singular values of H are basically square root of singular values of H Hermitian or H Hermitian H. Okay. Now this H Hermitian will be of dimension 3 cross 3 and this H Hermitian H will be of dimension 2 cross 2. So since this 2 cross 2 matrix is easy to handle, I'll first find out the eigenvalues of H Hermitian H. So this is a 2 cross 2 matrix. This is easy to handle. So we'll find out. So let me just write it. Step 1, we will find out the eigenvalues of the matrix H equal to H Hermitian H. Okay. So this matrix H Hermitian H, it is given by, your H Hermitian is 192573 into 192573, and this comes out to be equal to 86, 74, 74 and 83. And now what we need to do is we need to find out the eigenvalues of this matrix. This is my A. And how do you find out eigenvalues of a matrix? So eigenvalues of A are solution to the equation, that is here the characteristic polynomial A minus lambda I, determinant of A minus lambda I equal to 0. Or let me just use the consistent notations. Determinant of A minus lambda I equal to 0. So what is my A minus lambda I? So A minus lambda I is equal to 86, 74, 74, 83 minus lambda I is your identity matrix 1, 0, 0, 1. So this is nothing but 86 minus lambda 74, 74 into 83 minus lambda. So therefore, determinant of A minus lambda I sorry. So determinant of A minus lambda I, this is given by 86 minus lambda into 83 minus lambda minus 74 square. So this comes out to be equal to 86 into 83 minus lambda times 86 plus 83 plus lambda square minus 5476, and if you simplify, this comes out to be equal to lambda square minus 169 lambda plus 1662, and what we want is this to be equal to so now we need to find out the solution of this quadratic equation. So we'll use the standard formula. So what we have, lambda equal to 169 minus b plus minus under root of b square, that is 169 square, minus 4ac, that is 4 into 1662 into your a is 1 divided by 2a. So this comes out to be equal to 169 plus minus under root of 21913 divided by 2. And then if you solve this, then your lambda 1, which is nothing but your sigma 1 square, comes out to be equal to 158.515. So this is the first eigenvalue of your H Hermitian H, and lambda 2 comes out to be equal to, which is nothing but your sigma 2 square, that comes out to be equal to 10.485. Okay. So this is what we get. And mind you, your sigma 1 and sigma 2 should be in decreasing order. That is, the sigma 1 should be higher compared to sigma 2. So that's why we have written it in this form. So therefore, the singular values of H are sigma 1 equal to under root of 158.515. This comes out to be equal to 12.5903. And sigma 2 comes out to be equal to under root of 10.485. This comes out to be equal to 3.2381. Okay. So these are the singular values of your H. And okay, so if you want to get your sigma, so we have your H as U sigma V Hermitian. This was your 3 cross 2 dimensional matrix. This is 3 cross 3. This is 3 cross 2. And your V is nothing but 2 cross 2 dimensional matrix. So then your matrix sigma comes out to be equal to sigma 1, 0, 0, sigma 2, and 0, 0. Okay. So this comes out to be equal to 12.5903, 0, 0, 3.2381, and 0, 0. Now you have only two non-zero singular values. So your rank of H, which is the number of non-zero singular values, this comes out to be equal to. Is it clear? Any questions till this point? Okay, if there are no questions, then let me move on to the next question. So now it says that find the pre-coding vectors for the channel H in question 6. So what do you mean by pre-coding vector? Let me take you back to the earlier discussion that we have done. Yeah, when we were discussing your things, parallel decomposition. So when you want, so this pre-coding step is multiplying by a matrix V to your actual data, that is V. So your pre-coding vectors are nothing but the columns of your matrix V. So what we need to find is essentially the matrix V. And what is your matrix V? So V correspond to the right singular vectors of H, or those are the eigenvectors of the matrix H Hermitian H. So let me just repeat those things once in that particular question. Yeah. So here the pre-coding matrix, so let me just write it as matrix. The pre-coding matrix is V, where V comes from the singular value decomposition of your channel, and this V contains the eigenvectors of H Hermitian H, which we have already defined as V. So now what we need to do is we need to find the eigenvectors. So let's say this V has V1 and V2. Okay. And this V1 is the eigenvector corresponding to lambda 1 equal to sigma 1 square. which means that it will satisfy Vx1, sorry, it will satisfy AV1 equal to sigma 1 square V1. Similarly, this eigenvector V2 is the eigenvector corresponding to lambda 2 equal to sigma 2 square, which means that your AV2 is equal to sigma 2 square V2. Okay. So now to get your V1 and V2, we'll do the standard trick that we do in maths when we find eigenvalues. So we'll start with AX equal to lambda x. So your A matrix is H Hermitian H, and we already saw what H Hermitian H is. Here it is 86, 74, 74, 83. So this is 86, 74, 74, 83 into x1, x2, which is equal to lambda times x1, x2. So now this comes out to be equal to 86 x1 plus 74 x2 equal to lambda x1, and 74 x1 plus 83 x2, this comes out to be equal to lambda times x2. So this first equation here, what I can do is, so what I'll do is I'll represent x2 in terms of x1. Okay, so then that will give me x2 equal to lambda x1, or lambda times, sorry, lambda minus 86 x1 by 74. And in similar way, this will give me x2 equal to 74 x1 divided by 83 minus lambda. Now if you substitute lambda values, both of these equations will give me same value. We'll check that. Now let us first do it for lambda 1 equal to sigma 1 square equal to 158.515. So let's say this is equation 1, this is equation 2. So equation 1 will give me x2 equal to 158.515 minus 86 into x1 upon 74. This will give me 0.9799 x1. And equation 2 will give me x2 equal to 74 by 158.515 minus your lambda. Sorry, this is lambda minus 83. Yeah, minus 83 into x1. This again comes out to be equal to 0.9799 x1. So now what we'll do, I'll set x1 equal to 1, which means that my x2 will be equal to 0.9799. So now let's say my v1 tilde will be now equal to x1 into 0.9799. Now this vector tilde, or when I find its norm, this is not equal to 1. But now when we know that V is a unitary matrix, we need to convert it to a unit norm vector. So then what we'll do, this V1 is nothing but V1 tilde divided by norm of V1 tilde, which is nothing but 1 over under root of 1 square plus 0.9799 squared into 1 0.9799. This comes out to be equal to 0.7142 and 0.6999. Okay. Now this was for lambda 1. Now when we have lambda 2 equal to 10.485, then my equation 1 will give me x2 equal to minus 1.0205 x1, and same thing equation 2 will also give me a same thing. I'm not repeating the same things now. Now setting x1 equal to 1, I'll have x2 equal to minus 1.0205. So I'll have my v2 tilde equal to 1 and minus 1.0205, and so v2 is nothing but v2 tilde upon norm of this, so that is 1 plus 1.0205 square, and this comes out to be equal to 0.6999 minus 0.7142. So the combining matrix, the pre-coding matrix, therefore the pre-coding matrix it is V, which is equal to V1 V2. So this comes out to be equal to, your V1 was 0.7142, 0.6999, and your V2 comes out to be equal to 0.6999 and minus 0.7142. So this is your pre-coding matrix. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the next question. So the next question here says that find the pre-coding. Wait a minute. Yeah, sorry. There is a typo here. Yeah, not pre-coding. We now want to do combining matrix for the channel H in question number 6. So again, I'll go back to our discussion when we were discussing the contents of week 12. So we said that after we receive the pre-coded vector, let's say y tilde, what we do is we multiply the received vector vector by u Hermitian. So u Hermitian is basically our combining matrix. This u Hermitian is the combining matrix, and this u is the left singular vectors of H, or u is the contains the columns of u contain the eigenvectors of HH Hermitian. Okay, so let me go back to the question. The combining matrix is u Hermitian, and u is, this is a 3 cross 3 dimensional matrix, so I'll have u1, u2 and u3. These contain the eigenvectors of B equal to HH Hermitian. And eigenvectors of B equal to HH Hermitian are exactly equal to the eigenvalues of H Hermitian H. So what we have is this U1 is the eigenvector for lambda 1 equal to sigma 1 square equal to 158.515. Then this U2 is the eigenvector for lambda 2 equal to sigma 2 square, which is equal to 10.485. And U3 is the eigenvector corresponding to lambda 3 equal to 0. There are only two non-zero eigenvalues of HH Hermitian because it's a rank 2 matrix. Okay, so we have this now. So what we get here is your BU1 equal to sigma 1 square U1. Then this thing here will give me BU2 equals to sigma 2 square U2. And the third one here will give me BU3 equal to 0. Now let's say, yeah, equal to 0. So this is what we are having. So now what we want to deal with is your Bx equal to lambda times x. So now let us first use this particular relation which I just wrote to figure out the interdependent equations. Okay. So let's start. So Bx equals to lambda times x, where this B is your HH Hermitian, your H is 192.573 into 192.573, and this comes out to be equal to 26, 44, 17, 44, 130, 39, and 17, 39 into 13. Okay. So we have this. So therefore, Bx equal to lambda x will give me, I have my B, that is 26, 44, 17, 44, 130, 39, and 17, 39, 13 into x1, x2, x3. This will give me lambda x1, lambda x2, and lambda x3. So the three equations that I get is 26x1 plus 44x2 plus 17x3 equal to lambda times x1. Let's say this is equation 1. Then I'll have 44x1 plus 130x2 plus 39x3. This is equal to lambda times x2. 17x1 plus 39x2 plus 13x3, which is equal to lambda times x3. So this is equation 1. Then I have my equation number 2 and equation number 3. So what I'll do is, from equation 1, I'll write x1 in terms of x2 and x3. So that will give me x1 equal to 44x2 plus 17x3 divided by lambda minus 26. So let's say this is Roman number 1. From equation 2, I'll write x2 in terms of x1 and x3, and then I'll substitute x1 in that. Or rather, what I'll do, I'll first substitute x1 equal to this in equation 2. So 2 and 1 both imply 44 into 44x2 plus 17x3 divided by lambda minus 26 plus 130x2 plus 39x3 equal to lambda times x2. And now what I'll do, I'll represent lambda 2 now I'll represent x2 in terms of x3. So this will give me, if I simplify, this will give me 39 minus 748 upon lambda minus 26 times x3 divided by lambda minus 1936 upon lambda minus 26 plus 130. So this is the second equation. So I have x1 in terms of x2 and x3, and I have x2 in terms of x3. The third equation will also give me some relation which will again boil down to similar thing. But now to obtain x2 and x3, what I'll do is I will fix x3. So we will fix x3 equal to 1 and then get x2 and x1 using equation number Roman 2 and equation number Roman 1. Okay, so x3 is equal to 1. So now if I do that, then for lambda 1, which is equal to sigma 1 square, which is nothing but 158.515, I have x3 equal to 1, x2 comes out to be equal to 39 minus 748 divided by 158.515 into x3, that is 1. 158.515 minus 1936 upon 158.515 plus minus 26 is in denominator. Sorry, yeah, here also minus 26 minus I have plus 130. When I simplify this, x2 comes out to be equal to 3.2106. Okay, and similarly x1, it is equal to 44x2. So 44x2 is 3.2106 plus 17x3. x3 is 1. Then comes out to be equal to 1.1943. So therefore, u1 tilde, which is not of, which does not have norm 1, comes out to be equal to 1.1943, 3.2106, and 1. Yeah, sorry. Yeah, and this implies that u1 is nothing but u1 tilde upon norm of u1 tilde, and this comes out to be equal to, if you use your calculators, this will come out to be equal to 0.3347, 0.8997, and 0.2802. So this is u1. Now let us use lambda, the second one, lambda 2, that is equal to sigma 2 square, which is nothing but 10.485. Again, we have set x3 equal to 1. So x2 comes out to be equal to, so in this particular equation, we'll substitute 39 plus here. Yeah, plus. So we'll have 39 plus 748 divided by 10.485 minus 26 into x3, that is 1, divided by 10.485 minus 1936 upon 10.485 minus 26 plus 130. And this, if you simplify, this comes out to be equal to minus 1.7487. And then x1 comes out to be equal to, we have 44 into x2, that is minus 1.7487 plus 17 into x3 divided by lambda, that is 10.485 minus 26, and this comes out to be equal to 3.8636. So therefore, u2 tilde comes out to be equal to x1, that is 3.8636. Then we have minus 1.7487 and 1, which means that your u2, which is normalized vector, that is nothing but u2 tilde upon norm of u2 tilde, this comes out to be equal to 0.8867 minus 0.4013 and 0.2295. And finally, the last one is for lambda 3, which is equal to 0. So again, I have x3 equal to 1. So x2 comes out to be equal to 39 plus 748 upon lambda is 0, so minus 26 upon, I have lambda is 0, so minus 1936 upon minus 26 plus 130, and this comes out to be equal to minus 0.1842. And the next one is 44 into x2, that is minus 0.1842 plus 17 into x3 divided by lambda, that is 0 minus 26. So this comes out to be equal to minus 0.3421. So therefore, your u3 tilde is minus 0.3421 minus 0.1842 and 1, which means that your u1 is, sorry, u3 is u3 tilde upon norm of u3 tilde. So this comes out to be equal to minus 0.3189 minus 0.1717 and 0.9321. So therefore, your matrix U, which is U1, U2, U3, this comes out to be equal to 0.3347, 0.8997, 0.2802, 8867, minus 0.4013, 0.2295, then you have U3, that is minus 0.3189, minus 0.1717, and the last one is 0.9321. So this is your U matrix. So therefore, the combining matrix is U Hermitian, which is equal to the Hermitian of this particular thing. So that is 0.3347, 0.8997, 0.2802. Then we have 0.8867, minus 0.4013, and minus 0.1717. And the last, oh, sorry. Yeah, Hermitian. So 0.8867 minus 0.4013 and 0.2295, and the last one will be minus 0.3189, minus 0.1717, and 0.9321. Yeah. So this is your combining matrix. Is it clear? Any questions till this point? Okay, if there are no questions, then let me move on to the next question. So what is the capacity of the MIMO channel H in this particular question? So we have seen the parallel decomposition. So using the parallel decomposition approach, the capacity is given by C equal to summation I equal to 1 to 2 log 2 1 plus sigma I square pi into rho, which is equal to summation I equal to 1 to okay, this is basically log to the base 2 1 plus sigma 1 square p1 rho plus log of 1 plus sigma 2 square p2 into rho. Now your sigma 1 square is 158.515, so this comes out to be equal to log of 1 plus 158.515 p1 rho plus log of 1 plus your sigma 2 square was 10.485 p2 rho. So this is the capacity, bits per second per hertz. Any questions? Okay. If there are no questions, then let me move on to the next question. So next question says that find the optimal power allocation. So what I'll do is I'll start with this particular equation and not after substitution, just for simplicity. Okay. Okay. Yeah. And what I'll do is for this particular I will normalize rho to be equal to 1 just for the sake of doing it. And another thing that I'll do is I'll take two total powers. The first one will be P equal to 25 milliwatts and the second one will be 100 milliwatts. Okay, so let's do it. So the C now becomes your rho is equal to 1. So now I have log of 1 plus P1 sigma 1 square plus log of 1 plus P2 sigma 2 square. I'll construct my Lagrangian P1, P2 and lambda. So this will be equal to log of 1 plus P1 sigma 1 square plus log of 1 plus P2 sigma 2 square, or let me write it in a nice form. So summation I equal to 1 to 2 log 2 1 plus Pi sigma I square minus I have the power constraint, that is summation I equal to 1 to 2 Pi minus P. So this is my power constraint. Now I'll differentiate this with respect to ith power. So this comes out to be equal to log e to the base 2 divided by 1 plus pi sigma I square into sigma I square minus lambda pi. This I can write as log of e to the base 2 1 by sigma I square plus pi minus lambda, no pi here, and this I will set equal to 0. So then I get pi equal to log e to the base 2 by lambda minus 1 over sigma I square, and this I can write as 1 over gamma naught minus 1 over sigma I square. Okay, and so basically what we get is pi is 1 by gamma naught minus 1 by sigma I square plus, so max of 0 and this thing. Okay, so which means that my p1, okay, leave it. Yeah, okay, fine. So this is what we have. So now we'll do it one by one for both the transmit values. So the first one is your P equal to 25 milliwatts, which means that your P1 plus P2, which means your P1 plus P2 should be equal to 25 into 10 raised to minus 3, right? So what we get is 1 over gamma naught minus 1 over sigma 1 square, that is 158.515 plus 1 by gamma naught minus 1 over 10.485. This should be equal to 25 into 10 raised to minus 3. So 2 times 1 by gamma naught minus this thing is equal to 0.1017 is equal to 25 into 10 raised to minus 3. So this comes out to be equal to 2 by gamma. So therefore 1 by gamma naught is equal to 0.1017 plus 25 into 10 raised to minus 3 whole divided by 2. So this comes out to be equal to 0.06354. Now what we need to check is this 1 by sigma 1 square, it is equal to 0.0063, and 1 by sigma 2 square is equal to, if you simplify it, it comes out to be equal to 0.0954. Now this 1 by gamma naught, this is greater than, so this thing is greater than gamma 1, but this 1 by gamma naught is less than gamma 2, which means that, so if you remember the water filling algorithm, water filling diagram that we had, so we had this gamma naught and we have this gamma 1 by gamma naught. So anything that is greater than this 1 by gamma naught won't be allocated any power, which means that we need to now ignore gamma 1 and redo the calculation of gamma 1, gamma naught. Okay, so now what happens is, your 1 by gamma naught minus 1 by sigma 2 square is now equal to 25 into 10 raised to minus 3. And this is essentially your P2, which means that your P2 is now equal to 25 milliwatts, and you are allocating entire power to your second eigenvalue, the first eigenvalue. Oh yeah, I think I made a mistake. Yeah, ignore. Oh, sorry. This is greater than, what did I write? Yeah, 1 by gamma naught is greater than, I think I made a blunder here. Wait. 1 by gamma 1 is, sorry, 1 by sigma 1 square is 0.0063, and this is less than 1 by gamma naught, which means allocate power to gamma 1 to P1, and 1 by sigma 2 square is 0.0954. This is greater than 1 by gamma naught, which means that no power to P2. And here it should be 2, it should be 1, here it should be 1, and here also it should be 1. Okay, so you have your eigenmode 1, and then you have your eigenmode 2. This is your 1 by sigma I square. So sigma 1 by sigma 1 square is 0.0063. And this one is higher. So this one has a value of this one has 0.0954, and your 1 over gamma naught so if you solve this 1 over gamma naught, this will come out to be equal to 0.0313. So this is basically 25 milliwatt, which is equal to P1, and P2 equal to 0. So this is what exactly is happening when you are doing this butterfilling algorithm. So you are allocating entire power to your strongest eigenmode. Let me make a note of it. Entire power is allocated to the strongest eigenmode. Yeah. So this was the first part. Now let's move on to the second part. Now in second part, what we have done is we have increased the power. So the total power now we have increased to 100 milliwatts. So the second part, we have P equal to 100 milliwatts. So now we'll repeat the same thing. We'll now use the constraint. So power constraint gives us 1 by gamma naught minus 1 by sigma 1 square plus 1 by gamma naught minus 1 by sigma 2 square is equal to 100 milliwatts. That is 100 into 10 raised to minus 3. So this is 2 times 1 by gamma naught minus, we have same thing, 0.1017, which is equal to 100 into 10 raised to minus 3. So this comes out to be equal to 1 by gamma naught equal to 0.1017 plus 100 into 10 raised to minus 3 whole divided by 2. This comes out to be equal to 0.1008. Okay. Now we have 1 by gamma 1 1 by sigma 1 square. This is equal to 0.0063, which is less than 1 by gamma naught, and 1 by sigma 2 square, this was equal to 0.0954, which is also less than 1 by gamma naught. Now both of these values are less than gamma naught, which means allocate power to both P1 and P2. So then my P1, so therefore P1 will be equal to 1 by gamma naught minus 1 by sigma 1 square, that is equal to 0.1008 minus 0.0063. This comes out to be equal to 0.0945, which is simply 94.5 milliwatts. And yeah, yeah. And this P2 is simply your P minus P1, which comes out to be equal to 100 minus 94.5 milliwatt, which comes out to be equal to 5.5 milliwatt. And this also is equal to 1 by gamma naught minus 1 by sigma 2 square. Check. It will come out to be the same value. Okay, so now we have powers allocated to both P1 and P2. So how does the diagram now look? So same diagram I'm drawing. So I had mode 1, then we have the eigen mode 2, and then we have here 1 by sigma I square. This one, mode 1, had a value of, yeah, so this one was 0.0063, and the second one, so this one has a value of 0.0954, and your 1 by gamma naught now comes out to be equal to, so this is your 1 by gamma naught, which is equal to 0.1008. So then this much, which is equal to 94.5 milliwatt, is your P1, and this much, okay, yeah, sorry, small mistake, it's still, it's from here to here, yeah, and this one, the small distance, yeah, this one is your P2, which is equal to your 5.5 milliwatt. So now you are allocating powers to both the first and the second eigen mode. Is it clear? This is how your water filling, this is how you will be allocating powers to maximize your capacity. Now, small homework is you plug in those values and see how your capacity looks like. So what value of capacity you get, and then you also try with one thing, you equally allocate power, like P1 equal to P2 equal to P by half, that is total power by half, equally allocate and see how much difference you get at the capacity. So that will give you a flavor like how exactly your water filling algorithm is benefiting you in terms of improving it. Okay, So that's all I wanted to cover today. If you have any questions, then feel free to ask. Otherwise, you are free to leave the meeting. Thank you for attending today's session. Again, I'm repeating the announcement. There will be a summary session. It will be using the same link. You can join using the same link on October 12th, that is Sunday, from 3 p.m. to 5 p.m. So here I'll be revisiting all the concepts that were covered in this particular course. No question solving, just a simple revision before your exams. So thank you for attending all the sessions that I have covered, that I have taken for this particular course. Thank you again.